Okay, this is going to be our first lecture and mostly a review of algebra. The main ideas we're going to cover are linear equations, graphs, and the ever-dreaded word problems. So the problem we're going to look at this week throughout the lecture is in front of you there. So I have decided to retire from teaching and become a full-time widget maker. The fixed cost of a widget will be $100. The variable cost will be $5. I can sell them for $10, and I want to know what are the cost, revenue, and profit equations, as well as the break-even point. And we're going to look at tackling this problem in a number of different ways, just to show you how they all come together. Okay, so the first thing, and again, for many of you, a review, but the basic rules of algebra. Some have forgotten, some have not forgotten them, but I kind of lump them into three categories of easy, moderate, and difficult, relatively speaking. So you can read through that. Just it's the stuff you learned years ago, just the kind of mistakes you really do not want to make at this level. The most complicated of these is probably either the associative or distributive properties. So if you look there below and just make sure that you're comfortable with them. I'll give you a second. Okay. And the next thing is some of the translations between math and English. And this is kind of the basis of word problems, which most people seem to have a strong dislike for. So just to make sure that you know some of the kind of tricks of the trade, here's some of the ways you usually see addition, subtraction, multiplication, division, and powers displayed in problems. Again, the most common are probably product for multiplication and sum for addition. So just make sure when you see stuff like that that you know exactly which function they're representing. Okay, and here is the most common place where people make mistakes at this level, believe it or not, is the order of operations. Many of us learned it using the mnemonic, please excuse my dear Aunt Sally. So the order of operations are parentheses, then exponents, multiplication and division, moving left to right, and addition and subtraction, moving left to right. So if you plug through this example here, you should get an answer of -4. Many of you will not. So let's kind of go through it step by step here. So the first thing you want to do is solve each set of parentheses within the parentheses. So if we look at that first set of parentheses, within that you have a power and you have a subtraction. So you do the exponent first. 2 squared is 4. 8 minus 4 gives you 4. So that first parentheses is a 4. The second parentheses, within the parenthesis you have subtraction and multiplication. Multiplication comes first. So 2 times 2 is 4. 6 minus 4 is 2. So you have 3 times 4 plus 20 divided by 2 minus 3 squared times 2. Okay, the parentheses are gone, so the next thing you want to work through are the exponents. Okay, you have an exponent there at the very end, 3 squared, which is, of course, 9. So now we have 3 times 4 plus 20 divided by 2 minus 9 times 2. So the next thing is multiplication, left to right. 3 times 4 gives you 12. 20 divided by 2 gives you 10. And 9 times 2 gives you 18. And now what's left is addition and subtraction, again left to right, and that will give you an answer hopefully of -4. But these are good things to spend a little time on because again this is a very, very common place to make a mistake and really not where you want to make one. There are much better places to make them. Okay, so the next thing we're looking at are factoring and FOIL, which are kind of inverses of each other. If you remember, FOIL is multiplying two binomials, like you have here, 4x plus 3 times 2x minus 1. And I guess this is a lot of mnemonics for one lecture, but FOIL stands for you do the first terms, the outer terms, the inner terms, and the last terms. It's just a way to make sure that you remember to do all of the terms. Okay, and one thing to remember when multiplying different types of stuff together, if you have a binomial times a binomial, that's 2 factors times 2 factors, which is going to be 4 total factors before you reduce it. If you have a binomial times a trinomial, okay, which would be the first term has 2 factors, the second term has 3 factors, you're going to end up with 6 terms before you simplify. So you take the number of terms in each one, multiply that together, and that will tell you how many terms you're going to end up with when you multiply it out before simplifying. Okay, good thing to remember. And if you want to break down factoring in reverse, if you want to break down FOIL in reverse, sorry, that's called factoring. And as you could see here, if you wanted to go from 12x squared plus 2x minus 3 down to the simplest terms, what you need to do is you need to break down whatever's in front of the x squared and whatever is the last term using factor trees. And you need to do a little bit of trial and error until you end up with the right numbers. Okay. There are other ways to do this, but a lot of this is just trial and error. Okay, and this is just important when you're trying to solve an equation. You need to break it down into monomials and stuff without powers. It's just much easier to solve. You're going from quadratic equations to linear equations, and then it's easier to deal with. So that's why you do it, and we'll see more of that a little bit later on. Okay, and one of the reasons we like to break things down from quadratics to linear equations are linear equations are easier to graph, okay, which is kind of the next section here. Generally, linear equations, actually I will say all linear equations can be broken down into the form y equals mx plus b, where m is the slope of the equation, x is going to be the independent variable, and b is the y-intercept. Okay, so if you have y equals 2x minus 1, we know the slope of that is going to be 2. The y-intercept is going to be negative 1. Okay, and you can see that in the graph below. Okay, and as I mentioned, the key parts here are the slope and the y-intercept whenever trying to graph an equation. Okay, and sometimes we need to go the other way. On the prior slide, we went from equation to line. Sometimes you want to go from line to equation. And if you need to figure out the equation, the first thing you want to do is choose a couple of handy points and find the slope. Once you find the slope and you have one of the points, then you could easily kind of backtrack into the equation. So in this case, using the points 1, 1, and 0, negative 1, we can see that the slope is going to be 2. And choosing either one of those points, we're going to get the equation y equals 2x minus 1 after a little bit of algebra. Okay, and sometimes instead of seeing something of the form y equals mx plus b, we'll see something written as f of x equals mx plus b. Okay, and what's the difference between these? Absolutely nothing. Okay, so don't be afraid when you see something like this. Sometimes it's easier to use functional notation because you could look for y at a specific point. It's just easier to write it as f or function of that particular point. Okay, it's more of a just bookkeeping thing, but it's not unimportant. So if I ask you what is f of 3 here, all you do is wherever you have an x, you plug in a 3. Okay, just don't be confused. Don't multiply it. Sometimes you see a 3 in parentheses and you think you need to just multiply it out. All that means is you substitute for the independent variable with the number in the parentheses. Okay, and sometimes we have something called composite functions, which are functions of functions, which again sounds complicated, but really it's just bookkeeping. Okay, so if you look at the example I have here, you have f of x equals 2x plus 3, g of x equals x plus 3. So I can ask you, what is f of g of x, which by the way is how you read that. And the second one is, what is g of f of x? Okay, all you need to know is you want to work from the inside of the parentheses out. Okay, so in this case, f of g of x means wherever you have an x in the f equation, you're going to substitute in g of x. Okay, here g of x equals x plus 3. So again, all bookkeeping, nothing but bookkeeping. So if you put an x plus 3 into that equation for f of x, you get twice x plus 3 plus 3, which gives you 2x plus 9. And just on your own, you can confirm or deny whether g of f of x is going to give you the same answer. And just as a hint, it will not, but sometimes it will. In this case, it does not, though. Okay, and this is all kind of leading, now that we've dabbled in different types of equations and representations of them, how to solve the equations. Okay, there are two approaches that you can take. One is using algebra, and one is graphing the equations. Okay, and here's kind of the correlate of how they connect. Okay, so if you have two lines intersect at a single point, that means you have two equations with a single solution. If you have lines that run parallel, it means they never touch. It means there are no solutions. These are called inconsistent equations. And the third different possibility you have, both graphically and algebraically, is when you have two equations that actually give you the same line. That means there's infinite solutions. And these are known as dependent equations. Okay, and I have an example of each there. So let's jump into that. Okay, so what is the solution of y equals x plus 2 and x plus y equals 1? So what is the solution of that set of equations? Okay, and if you wanted to graph it, and I gave you a deliberately blurry graph, so it wouldn't be too easy to read these solutions. Okay, so this is what it would look like. What you can see clearly from the graph is they are independent equations. They have a single solution, okay, which is nice. One thing that a graph can always tell you is what you're dealing with. You should be able to tell pretty quickly whether you have a unique solution, no solutions, or infinite solutions. That's a good thing to read off a graph. Once you do that, if you want to get a little bit more detail, what you do is you solve each of the equations for the same variable, and then you can set them equal to each other. So the first equation is already solved for y. If we want to solve the second for y, we subtract x from both sides. So that gives you y equals 1 minus x. So you set 1 minus x equal to x plus 2, and you get a solution of y equals 3/2. And this is also nice to have a graph because you could see, is y equals 3/2 plausible? And if you look at the graph, you can see that, yes, it's a plausible solution. Okay, and if we wanted to try a slightly different approach to the same equation, okay, which is called the addition method, what you want to do is you want to solve both equations with the variables on one side. I guess not solve, but you want to set up both equations with the variables on one side and the numbers themselves on the other side. And then you want to line them up, and you want to see what you can do to eliminate a variable. Okay, sometimes this is easy, sometimes this is difficult. In this example, it's pretty easy. When you add them together, the x's drop out. So you get 2y equals 3, or again, y equals 3/2. Okay, where things get a little bit more complicated is when you have more than two equations. And this is a good time to mention, if you have the same number of equations as you have variables, you will have a chance of having a unique solution. If you have more variables than equations, you will not be able to get a unique solution. So just keep that in mind. So in this case, we have 3 variables, 3 equations. That means we have a chance at getting a unique solution. And the approach we're taking here is a little more ad hoc. So you want to take 2 equations and see if you can, using those 2 equations, get rid of a variable or so, and then kind of backtrack and see if you can manipulate things into a way where things have solutions. Okay, so looking at the approach I took here, okay, the first and second equations, you add them up, you get rid of the z. Okay, and then if you can also get rid of the z between another set of equations, in this case the first and third equations, then you have something you can deal with. Okay, so you have 4x plus y equals -14. from the first and second equations, using the first and third, you get 8x plus y equals negative 30. Okay, now you solve it using the approach from a couple of slides ago. You have x equals negative 4. You could plug that back into one of these two equations, solve for y, and get y equals 2. And then finally, you could substitute it into any of the original equations, and you could find out what z is. Okay, so our solution set here is negative 4 to negative 1. Okay, and if this seems a little bit ad hoc, it's because it is completely ad hoc. But what we're going to do next week is we're going to find a much more methodical approach to solving multiple sets of equations. Okay, so let's look back at the problem at the top of the lecture. We had Dr. Phil as a widget maker, a professional widget maker. Okay, so our two equations for cost, we had 5x plus 100. Okay, again, the variable cost is the cost per, so that's 5 times the number you're creating. 100 is the fixed cost, so that does not have a variable attached to it. And the revenue is 10 times the number you sell. Okay, so let's graph these using this beautiful graph done in Excel. Okay, you can kind of read things off here. Okay, sometimes it's easy to tell, sometimes it's not. From this graph, you could see that the break-even point is 20 widgets with a cost of, or a revenue of $200. Okay, and again, you can see we start off before that with a higher cost and we end up with a higher revenue. Okay, the red is the revenue, the blue is the cost, and you can see how they fluctuate there. Okay, and for your own benefit, if you wanted to solve it algebraically, which clearly I did not do here, you would come up with the same answer. So next week we'll cover a much more methodical approach to solving multiple sets of equations, but hopefully this is something that made sense as either a review or just something, a different way to look at something you've learned before.